Hello students, welcome to Royal Chem Chemistry classes. So today we are going to discuss about one of the important portion in coordination chemistry, that is color theory of in coordination compounds. Okay, so this topic color theory, there are so many questions asked in previous year CUT, JAM, GATE and NET. It's a very important concept, very important topic. So that so many questions asked in previous year exam. So let us discuss about the color theory of the coordination. So basically color theory means that we know that most of the coordination complexes are colored. Why they are colored? That is what we are going to discuss here. So why it is colored? Because if you look at any coordination complex, so there is some electronic state present in this molecule. So basically electronic state, that you have a ground state electron state and you have excited state electron. If an electronic transition, if the transition from the ground state into excited state is happened by the application of the suitable electromagnetic radiation, especially UV visible rays, electromagnetic radiation, then some kind of excitation will occur from the ground state to excited state. Due to this excitation, if it is in a visible ray, we will get a color is due to the we will get a color. Now this color is due to basically what? Electronic transition. Electronic transition from the ground state to the excited. As a result, we are getting color. Okay. Now the question will arise is that all electronic transition leads to color? But answer is no. That means but all transition are not allowed. Why all transition are not allowed? Because there are some selection rule. If those molecules that follow that selection rule, then only it will show color. So the selection rule is that basically you have two selection rules. First one is Laporte selection rule. Second one is screen selection rule. So Laporte selection rule means what? So before going to Laporte selection rule, I will come to this point. If you have more number of transition, if in a molecule, if you have more number of transition from the ground state to excited state, then you can say that allowed transition, if you have more number of allowed transition from ground state to excited state, you can say that that molecule will show more intense color. That molecule will show more intense color. This point you have to remember in mind while dealing with the color theory. Now let us come to the our point, the selection rule. So basically the selection rule, we have Laporte and screen selection rule. So Laporte selection rule, Laporte is one. According to Laporte selection rule, Laporte allowed transition will show more intense molecule. So those molecules which will show more, which will follow Laporte transition, Laporte rule, that molecule will show more intense color. So from this we can conclude that if some dissymmetry present in the molecule, I will come to what is dissymmetry. If dissymmetry is present in the molecule, which is directly proportional to number of transition, which will directly related to color intention. That means if some dissymmetry, the dissymmetric state present in your molecule, more the dissymmetry, then that is more number of transition is there. If you have more number of allowed transition, then definitely color will more intense in nature. That is what this point is called. So actually we have to discuss actually what is Laporte selection rule. So suppose you are in a molecule ground state electronic configuration, electronic state in an un-Girard symmetry. U means un-Girard. You learned this from the chemical body, and excited state also un-Girard. According to Laporte selection rule, that un-Girard to un-Girard transition is not allowed. That means Laporte's forward. Similarly, if you take if your ground state is un-Girard and excited state is Girard, this transition is allowed. And if you go to another state, if your ground state is s orbital and excited it is s orbital, that is also Laporte's orbital. Now if you have p is the ground state and p is the excited state, that transition also Laporte's orbital. If you are most importantly, we are dealing with the dt transition. So you may ask that why dt transition is not that much intense color. dt complexes are octahedral dt complexes are why less intense color. That is due to this reason, because d to d transition is also not allowed according to Laporte's selection rule. Similarly, if you look at the p to s, if you have ground state p and excited s, then according to Laporte's rule, what Laporte said, this transition will allow. Similarly, if you have p ground state and d is your excited state, then also the transition is allowed. So from this you can understood that those allowed transition G to U and the S to P and the D to D, P to D. All these you can see that the ground state is U and the excited state is G. That means the symmetry of the ground state and the excited state is different. That is the meaning of the dissymmetry. If in your electronic state you have more dissymmetry, that means the transition will be allowed. If you have that number of allowed transition is there, then definitely color intensity will increase. So dissymmetry means nothing but the excited state and ground state symmetry will be different in matter. Okay. So from this allowed transition from U to G, similarly P to S and P to D, you can clearly see that there is some difference. If you take the delta L value, from these 3 points I can conclude that if I have delta L, L means unit spin orbital angular momentum number. If delta L value is 0, then it is forbidden. You look in delta L value, U to U, both you have same L value so 0. S to S. S to S, L value is 0, S also L value is 0, so delta L will be 0. Similarly for P, delta L value should be 0. If delta L is 0, then we can say that it is forbidden. If it is forbidden, then definitely the transition is not allowed, then it will not give any color. Now if you look at the P to S, P to S, you know that P for P L value is equal to 1 and S L value is equal to 0, so delta L will be equal to not is equal to 0, it should be in plus or minus 1. If it is plus or minus 1, then we can see that allowed transition. So this is for Laporte selection. If your delta L value is equal to 0, then Laporte is forbidden. If your delta L value is equal to plus or minus 1, allowed transition. Okay. So this is all about the Laporte selection rule. Now let us discuss about the spin selection rule. So spin selection rule is similar to Laporte selection. If delta S value is equal to 0, then only it is allowed. It is not similar to Laporte selection rule, just reverse. Okay. If delta S value is allowed, then only it is spin selection rule. Upon the spin selection, delta S value is allowed, then we can observe the allowed transition. If delta S value is equal to not is equal to 0, we can see that the transition is forbidden in nature. So let's discuss about the spin selection rule more detailedly. That means if your delta S value, spin changes spin value is equal to 0, then we can say that it's a spin allowed transition. If spin delta S not is equal to 0, then we can say that spin forbidden. Spin is forbidden for the transition. So for example, let's say if you have example here D1 electronic configuration in octahedral field T2G EG orbital is there, T2G 1 electron is there. So while transition let's say 1 electron is excited to the EG state. So after excitation we will get the 1 electron is here, this here. So in this state, before the transition we know that only 1 electron, that S value is equal to 1 by 2. And after excitation also we have only 1 electron at the EG orbital, then we can have S is equal to 1 by 2. So in both state electron, total spin of the electron is 1 by 2. So delta S value is equal to 0. If delta S value is equal to 0, then we can say that this is spin allowed transition. Okay, so let's say second example for the spin forbidden transition. If you have D5 I spin complex, then you have T2G orbital here, then you have EG orbital here, 5 electrons is there. So total spin is equal to 5 by 2. One spin value is equal to 1 by 2. So total 5 electrons are there. So S is equal to 5 by 2. So let's say if this electron is excited from the ground state to the excited state. So definitely what will happen that this electron spin will change, it will pair up according to Pauli's exclusion principle. Okay. So S value is equal to, then in this case S value is equal to 3, for this S is equal to 0, so remaining we have 3 electrons. So S value is equal to total spin is equal to 3 by 2. So before transition we have total spin value is equal to 5 by 2, after transition we have 3 by 2, because 3 by 2 is contributed from these 3 electrons. This already goes to 0, plus 1 minus half. So ultimately delta S value is equal to 0, then we can say that is a forbidden transition. So important point is that if the spin allowed transition is there, just like Laporte selected allowed transition, if spin is the allowed transition is there, then we can say it's a more intense in color. Okay. So from this Laporte selection rule and spin selection rule, we can conclude that if the spin allowed transition, similarly spin Laporte allowed transition, then we can say that that molecule is more intense in color. Okay. Now we have to remember one of the important points. We have already discussed about the Laporte selection and spin selection rule. So while comparing these two selection rules, we have to remember one important point. That means let's say if I have a octahedral complex and a tetrahedral complex, both are given there. So we know that in octahedral complexes we have T2G orbital, EG orbital. So basically T2G and EG orbital they are nothing but they are d orbital. So according to Laporte's selection rule, D to D there is no symmetry change. You can see here is a G, here also G, and both are d orbital. So D to D transition is not allowed according to Laporte's selection because delta L value is equal to 0. This is forbidden one. Okay. But if you look at the tetrahedral complexes, again you have on the state is d orbital, that is your E, and you have d orbital, T2 orbital excited state, that is excited as a T2. But again, the ground state is a D, but excited state configuration orbital is basically not completely D character. It is a PD mixing character. D is mixed with P is mixed with the D orbital. Why it is happened? Because tetrahedral complexes are non-centrosymmetric molecules. That means they don't have any symmetry, less symmetry in nature. So due to that, from molecular orbital energies are very similar to each other, so that they can mix. They can mix each other. So finally, ultimately, you are getting excited state orbital having both P and D mixing character. So if excited are having P to D mixing and ground state is D, so you can say that the transition is possible, but not completely allowed transition. You can say that the Laporte partially allowed. But in octahedral it is completely forbidden. Why? Because both are D character. But here ground state is D and excited is PD character, P and D, little bit P character case. So as a result, it's a Laporte partially allowed transition. Due to this, it can octahedral complexes are more intense in color. Okay. So example also we can write from here that octahedral complexes is less intense compared to tetrahedral complexes. Why? Because in octahedral complexes Laporte is forbidden and tetrahedral complexes what they are Laporte partially allowed because of the PD mixing. So this point is very important. Okay. So we can conclude that basically all DD transition is Laporte forbidden in nature only. That is why they are less intense color. But among the octahedral and tetrahedral, if you compare, then tetrahedral is more intense compared to octahedral because of the some PD mixing character occur in the excited state of the tetrahedral complex. So some example, one of the examples given here, you have cobalt 8265. So octahedral complexes, cobalt in +2 oxygen state. It is pale pink color. Pale means less intense color, pink color. Similarly, we have cobalt Cl4 2-. It gives deep blue color, deep blue. Why? Again, cobalt is +2. Why this is deep blue color? Why this pale pink color? This is due to this Laporte partially allowed transition is possible in tetrahedral complex, but not possible in octahedral complex. This is the reason. This point you have to remember while dealing with the color theory. Now let us summarize the what we have already discussed so far. Laporte's allowed Laporte's selection rule and spin selection using a table. Okay. So in table I have given for different column. First column we have Laporte selection, then spin selection, the type of transition in which molecule will show, what kind of compound it will, which kind of compound which will show the transition, then color intensity, nature, then finally example. Okay. The first condition in Laporte selection rule, if it is Laporte allowed, your transition Laporte allowed, and spin selection rule, if it is spin allowed, then you can say that the type of transition is charge transfer transition. We will discuss it later. Okay. The compound is basically charge transfer compound, and the intensity is most intense. Definitely we know that if transition is Laporte allowed and spin allowed, definitely its color will be most intense nature because it is allowing both the selection. It is satisfying both selection. And in another way, you can say that molar excitation coefficient will be high for such kind of compound. Because in UV visible, basically this color of the coordination complex is studied by UV visible spectroscopy using Beer-Lambert's law. You know that Beer-Lambert's law of A is equal to epsilon into C into A. A is equal to absorbance, epsilon is equal to molar extinction coefficient. Basically this value molar extinction coefficient indicates the intensity of color. More the value of epsilon, you can say the most intense color. So in charge transfer compound you have higher the value of molar extinction coefficient. Okay. So example for these charge transfer complexes is potassium permanganate, cadmium sulfate, and many other examples are there. We will discuss when we will discuss about the charge transfer spectra. And second condition is the Laporte is partially allowed and spin allowed transition. Similarly, this type of transition, DD transition, but the little bit difference that where your excited state is PD mixed character. So you just remember where we introduced the PD mixing in tetrahedral complex. So due to this, Laporte partially allowed, it showed more intense color. Okay, the example is cobalt Cl for 2 minus. And third case is we already discussed Laporte allowed and spin allowed and partially allowed and spin allowed. Okay, now third case is Laporte forbidden but spin allowed. So again, it is a DT transition where you will get Laporte forbidden. You know the spin allowed, you will get in an octahedral compound. Octahedral compound, since it is a spin allowed, so little bit intensity is there, that is why it is less intense. Example is cobalt H2O 6 times 2 plus. Okay, so these two examples we discussed when we comparing the octahedral and tetrahedral color intensity. The last one you have Laporte forbidden and spin forbidden. Definitely it is a DT transition compound. You can see that if it is a Laporte forbidden and spin forbidden, definitely it will be very less intense color. So example is compound is D5 high spin complexes. D5 high spin complexes will show the Laporte forbidden spin forbidden. So its intensity is least intense. That means you can say that epsilon value is very less, very low value epsilon. Okay, here we have more intense. Let's say epsilon molar extinction coefficient. Epsilon molar extinction coefficient is very low here. And example is manganese H2O 6 times 2 plus. Here you know that manganese is a D5 electronic configuration because manganese in +2 oxidation state D5 high spin complexes. Okay, what is the weak ligand? It is a D5 high spin complexes. So we have already discussed that it is a delta S is equal to not is equal to 0, and also we know that delta L is equal to not is equal to 0. Delta L is equal to 0 because it is a DT transition. Octahedral complex will show DT transition. So both selection rule is not satisfying, that is least intense flow. So this is what is summary of the Laporte and spin selection. If you have able to memorize or if you understood this table very nicely, then it is sufficient enough to crack your any question based on the color theory. Okay. Now let us discuss about the charge transfer spectra. Okay. Charge transfer spectra, we have already know that charge transfer spectra complex is a highly intense color because it will show Laporte allowed and spin allowed transition. It's a very important topic. Many times in examination question asked in this topic. Okay. So generally charge transfer spectra is two types of charge transfer spectra is there. One is LMCT, the second one is MLCT. So LMCT is the name itself indicates that ligand to metal charge transfer. That means if you have compound, coordination compound, then from ligand filled orbital to metal vacant orbital charge is transferred, then we call it as ligand metal. Similarly, in MLCT, if you have a compound MLN compound, from the metal filled orbital to ligand empty orbital, if charge is transferring, then we can call it as metal to ligand transfer, that means MLCT. So now I am discussing about the LMCT charge transfer spectra on DPD. So LMCT charge transfer, ligand to metal charge transfer. Okay, that means if you have ligand and you have metal, basically metal ligand will be a pi donor ligand. Ligand is a donor, so but it should be a pi donor ligand. Pi donor ligand, you know that from coordination chemistry, halides, oxides, sulfates, halides. These all are pi donor ligand. They have p orbital. Using that p orbital, they will donate to metal through pi man. And acceptor, basically definitely metal should be accepted. Since ligand is donating to metal, so metal should be accepted. So metal should be accepted. So where it will go electron into metal d or s orbital. Why metal d orbital, s orbital? Because the ligand is already p orbital. Metal should be d. Metal should have d or s orbital because it should follow Laporte allowed transition. That is delta is plus or minus equal to 1. So we know that charge transfer spectra is Laporte allowed. So in order to start this, definitely should be metal vacant orbital d or s because pi donor ligand already have p orbital is a donation symbol. So then we can say that it's a delta L is equal to plus or minus 1. Okay. So example. So basically this metal electron division. There are two kind of LMCT transition occur. First one is the P to D LMCT. Second one is P to S LMCT. That means if you have a ligand p orbital, pi donor ligand p orbital and metal d orbital, vacant d orbital, then we can basically metal d0 forward. Okay, this kind of LMCT we know as P to D LMCT. ligand p orbital, pi donor ligand p orbital, metal vacant d0 orbital. Okay, so this kind of transition is known as P to D LMCT. So example is potassium permanganate. Potassium permanganate, you know that manganese is plus 7 oxygen state, that D0. So metal, we have ligand oxide ion. So oxide p orbital will donate electron density to electron charge into the vacant d orbital of manganese. So you can see that P to D transition is that delta L is plus or minus 1. So for alloy, Laporte's alloy, that's why it is a dark purple color. Similarly, another example is potassium permanganate. Okay. So P to D LMCT is off. Now P to S LMCT, from ligand pi donor p orbital to metal vacant s orbital. So generally, if you take the example is cadmium sulfate. Cadmium sulfate is a cadmium plus 2 is oxygen state. So this D10S0 configuration. So in this case, sulfur filled p orbital is a pi donor ligand. Filled p orbital electrons charge or electron will transfer into vacant s orbital of the cadmium. So this kind of transition we known as P to S. Again, it is following delta S plus or minus 1 condition, that is Laporte's law. So cadmium sulfate is also highly intense color because to P to S LMCT. So basically the LMCT, P to S LMCT, the pi donor ligand is highly energetic pi donor ligand. You know that sulfur and iodine, they have little bit electron activity is a little bit low. So the pi donor ligand orbital will be in a higher energy manner because we are donating electron to S orbital. So that we can see that the higher energy high energy pi donor ligand like sulfur and iodine is preferable for the P to S LMCT, not like oxide ion. Oxide ion is preferable for the P to D LMCT. Oxide ion kind of ligand, pi donor ligand is favorable for the P to D LMCT. Okay, so this is what about the general idea of the LMCT transition, LMCT charge transition. Now let us discuss about the one important concept is the LMCT energy. Okay, so many time question is asked based on the LMCT energy. So LMCT energy you can easily understood by using a small MO diagram. Okay, so you have metal here, you have ligand here. So for bonding, you know that metal ligand loop orbital will interact with the metal d orbital. So metal after the bond construction, you know that metal ligand group orbital will be in lower energy pi donor, and you have metal e orbital and metal T2 character orbital. So LMCT is basically nothing but ligand pi donor to metal e orbital transition. Sometimes T2 transition also there, but generally ligand pi donor basically is a p character orbital. So pi donor to the ligand e orbital, this energy gap is known as metal e orbital. This energy gap is known as LMCT energy gap. Pi donor ligand pi donor to metal e orbital, this energy transition, this energy gap delta is known as LMCT energy gap or LMCT energy. Okay, so you have to only remember this concept. So using this delta energy, delta E LMCT energy, we have to conclude some point. So basically the important point is that delta is directly inversely proportional to intensity of color. The delta is inversely proportional to lambda max. We know that delta is equal to h mu, which is equal to hc by lambda. So delta is directly proportional to frequency also. The delta is inversely proportional to oxidation state of metal. So this is the most important. All these 4 points concludingly I put it in a box that intensity is equal to is directly proportional to lambda max, which is directly proportional to oxidation state of metal, which is inversely proportional to delta. This table you have to remember. Okay, so using this concept, let's say if you have metal plus 3 and plus 4 and plus 5. So energy wise we know that higher the oxidation state, electronegativity will be higher in nature, so it should be lower in energy. That is why plus 5 energy is lower, then plus 4, then plus 2. Then you have ligand, of course ligand orbital energy is always lower because ligand we consider as a generally electronegativity, higher electronegativity compared to metal. That is why ligand group orbital energy is coming the downer side, out side. Okay, otherwise we won't have LMCT energy transition. Okay, because ligand is from lower to from ligand orbital to metal e orbital transition. Okay, that is why it is LMCT energy. So from this you can see the transition. If ligand is given already here, you have plus 5 plus 3. If it is plus 5 to transition E1, then plus 4 to E2 and plus 3. By looking this energy gap, you can see that E3 energy is higher than E2 than E1. So higher the energy, that means lesser the energy. That means you can say that higher the energy means for M plus 3, ligand plus 3 energy intensity will be low because they are inverse relation. So using this concept, let's do this question. It's asked in previous year JAM, GATE, NET and even CUT exam. Many exam this kind of question, asked. The question asked is the increasing order of intensity. So the vanadium oxide, you know that if you took the oxidation state, vanadium is plus 5, chromate is plus 6 and manganese is plus 7. So using this concept, high oxidation state concept, this that you know that higher the oxidation state, lower the LMCT energy. Okay, or intensity relation of intensity is directly proportional to oxidation state. So definitely, so C is greater than B is greater, A is greater. Because C is higher oxidation state, that is why intensity is high. If someone asks what about the lambda max relation, lambda max is also direct same relation. Intensity is directly proportional to lambda max, that is equal to oxidation state. That means intensity also C is greater than, lambda max also greater than, C greater than, B greater than. If someone asks the LMCT energy is inversely proportional to oxidation state, so the order will be reversed. A greater than, B greater with related to LMCT energy. Now this is another example using LMCT energy concept. So you are given that manganese oxide and technetium oxide and rhenium oxide. The question asked that intensity order. Again, intensity order. You see. So question asked what is the intensity order. So if you look at these three examples, all are in same group. Manganese, technetium, rhenium, all are same group. So all are same group. So oxidation state is also same because manganese here plus 7. Only difference that their d orbital is different. Manganese has 3d, technetium have 4d, then rhenium have 5d. So if you discuss about the LMCT transition here, we have pi orbital, ligand to p orbital is all are in same energy level. Then we have metal 3d, manganese metal 3d is somewhere here, and technetium because 3d is 4d is higher energy than 4d, so its energy is little bit high. Then 5d energy is high compared to 4d and 3d. But ligand orbital is same energy. Now if we compare the energy, transition energy, so pi to 3d, a ligand 4d, a ligand 5d, you of course this delta is very high. This is very high nature. So if it is very high nature, we know that intensity relation delta is directly inversely proportional to intensity. Intensity and delta is inverse relation. Okay. So you can say that intensity is equal to in case of intensity where we have more intensity. In case of manganese we have more intensity because its energy gap is very low, that's why intensity is high. So A is greater than, B greater than C. That is the intensity relation. If someone asks lambda max, then lambda max is equal to lambda max is directly proportional. Again A is equal to B greater to C. Then delta E is directly proportional to how? Energy 5d and 4d. So from this conclusion we can see that delta is directly proportional to more than 5d than 4d than 3d. That means if I have 5d orbital, then I have more delta E than 4d and 3d. Okay, so the answer is here C greater than, B greater than D. So concludingly, the 2 points we have important that delta is the inversely proportional to oxidation state and delta is directly proportional to 5d is greater than 4d and 3d. And these all together, finally we have a table here where intensity is directly proportional to lambda max, then it is directly proportional to oxidation state, it is inversely proportional to delta E, which will directly related to 5d and 4d, 3d. So this table you have to remember. Okay. So this is all about the LMCT charge transfer spectra. Now let us discuss about the MLCT energy transfer, charge transfer. So MLCT charge transfer, you have metal. So from metal to ligand orbital charge transfer. So basically metal is a donor, a ligand is an acceptor. So it is a donor, since metal is a donor, should have high d electron density and should be in lower oxidation state. So since metal is a pi acceptor means it should accept electron. So basically those ligands which are pi acceptor ligand, they are considered as the MLCT charge transfer spectra. So example is carbon monoxide, cyanide and phenolphthalein bipyrite. These all ligands basically show MLCT charge transfer spectra. So examples are that you have chromium CO6 type, You have vanadium CO 4 times and phenanthrene. You have Fe bipyrimidine 3 times 2 plus. Here basically you can see that this is a pi acceptor ligand. This one is pi acceptor ligand. Bromine is 0. Here also vanadium is 0 oxygen state. Here also iron and bipyridine. This is also pi acceptor ligand. Iron is in plus 2 oxygen state. Still it has sufficient electrons. So these all are MLCT ligand charge transfer examples. Okay. So this is what about our charge transfer spectra. We have discussed about the charge transfer. We have discussed about the MLCT, LMCT, and startingly we started with the color theory. Where color theory we were discussed about the Leporto selection rule, then Sven selection rule. Then we have discussed summarized the table with the more example. Then after that we discussed about the charge transfer spectra. In charge transfer spectra we have ligand to metal charge transfer. There we have two type of ligand to metal charge. One to P to D. Then P2S charge transfer spectra. P2D basically metal in D0 oxygen state, and P2 is where metal in 0, sulfur with 0 electrons. Okay. So after that we were discussed about the LMCT energy gap, and then finally we discussed about the MLCT concept. See, these all about the color theory of the transition compound. Okay. So now we will discuss about some of the example asked in previous year QSAT and GATE and NET exam. Okay. Okay. Now let us discuss about some of the previous year exam question asked in QSAT and IITJAM and GATE exam based on the color theory and the charge transfer spectrum. The first question is the correct order of LMCT energies. The 4 options is given that this we have already discussed while discussing about the LMCT. Okay. So we know that the important point we know that delta E is inversely proportional to oxidation state. Okay. Higher the oxidation state, lower the energy. So among manganese we have plus 7, manganese is plus 7, and bromine is plus 6, and vanadium is plus 5. So higher the oxidation state, lower the LMCT energy. So definitely manganese O4 are higher the oxidation state is lowest energy, then bromine and vanadium. So A is the correct option. We have already discussed this. So second question. Okay, second question, according to crystal field theory, DD transition observed in titanium H2O systems. So titanium H2O systems is octahedral complex. So definitely we know that octahedral complex is whole octahedral complex DD is Laporte's formula because delta L is equal to naught is equal to delta L is equal to 0, that is in Laporte's formula. So DD transition, first of all we understand that this is a Laporte's forbidden. So Laporte's forbidden option we can have either we can have this or either we can have this, won't be the answer. So second condition, whether it is spin allowed or spin forbidden, because the titanium is 3 plus a D1 electronic configuration. So D1 electronic configuration we know that delta S value is equal to 0 because we have already discussed this one. So D1 is delta, we have already discussed in the past. D1 is delta S is equal to 0. If it delta S is 0, it's the spin allowed transition. Spin allowed transition. Okay. So among these two options, or two options, Laporte's forbidden and spin allowed. That means the D is the correct answer. D is the final correct answer. Laporte's forbidden and spin allowed. Okay. Now the third question is that correct order of increasing intensity or molar absorptivity of the UV visible absorption band for the ion titanium H2O 2 plus, manganese H2O 2 plus, and chromium oxide 2 minus, and nickel Cl4 2 minus. See the correct intensity order asked in question. Okay. So we know that intensity, most intensity color is always charge transfer spectrum. Okay, charge transfer spectrum. So we know the charge transfer spectrum. So CR04, CR, if you look at the CR, it's a plus 6088, D0, the O4 you have O2 minus. So definitely it is LMCT energy transfer. So it should have higher the intensity. Now if you look at the option, there are two options. B and C, where we have C or O4 is higher intensity, higher the order of intensity. So A and D will not be our option. So this is known as elimination method of solving problem. Elimination method. Okay. Okay. Among B and C, we have to look for the another. Now we have titanium H2O, manganese, and nickel Cl4. So nickel Cl4 is a tetrahedral complex, and these two are octahedral complex. And tetrahedral complex are higher intensity than octahedral complex because tetrahedral complex is a Laporte's partially allowed because of PD mix. So now among B and C, we know that okay, this option NaCl4 is the greater compared to octahedral complex. So this one is the correct one. And C option we don't have we have C is the nickel C4 is the least one. So B is the correct answer. So we got the charge transfer spectra is the higher intensity, then tetrahedral. Then among the octahedral complexes, this one manganese is completely less intense because it is Laporte's and is spin forbidden. Then titanium is a spin allowed. Okay. So B is the correct answer. Okay. Now let us discuss about the another question. Another question is that given that the complex manganese H2O extends as very light pink color, the best reason for it is. Okay. So, 4 option is given here. The first option, complex does not have a charge transfer transition. Second, DD transition allowed, orbital forbidden, but spin allowed. DD transition here, orbital allowed and spin forbidden. And DD transition has both orbital and spin forbidden. So, we know that manganese H2O 6 times 2 plus, where manganese is in 2 plus oxygen state, that is D5 I spin. And all DD transitions are, we know that all DD transitions are Laporte's forbidden, that is orbital forbidden. So we understood that orbital forbidden. So orbital forbidden option is, first reason is that orbital forbidden. Second one, D5 I spin, also we know that delta S is equal to not is equal to 0. This we already explained during our classes. Delta S not is equal to 0, so it is spin forbidden. So it is both orbital forbidden and spin forbidden. That is the reason this is very late pink. So in option, you can see that the D option is the correct answer for this. DD transition both orbital, that means Laporte's and spin forbidden. As a result, it the light pink color. One more question we have regarding our charge transfer and color theory. We have cadmium sulfide and mercury sulfide and bismuth iodide are colored due to ligand to metal charge transfer and DD transition and metal to ligand and combinational ligand metal charge transfer and DD electronic transfer. Okay, so we know that cadmium sulfide and mercury sulfide and bismuth iodide. Okay, the cadmium is +2, that is D10S0, mercury is +2 oxidation D10S0, bismuth is +3 oxidation is also D10S0. So we have S2 minus a ligand, it's a pi donor ligand. You see p orbital, it will donate into S vacant orbital. Similarly, we have sulfide here, it will electron donate into the vacant S orbital, and iodide also here, it will donate electron to vacant S orbital. Basically, P to S electronic transition of the charge transfer is occurring. That is basically nothing but from ligand filled p orbital to metal vacant S orbital. That is ligand to metal charge transfer spectra is happening here. Okay. There is no D transition. Why? Because D orbitals are completely filled D10 configuration, so then there is no scope of DD transition. Only the color is due to because of charge transfer spectra, that is ligand to metal charge transfer spectra. So correct option is A is the correct option. Okay. So this is what all about our charge transfer spectra and color theory. So I am again repeating that in previous year exam, if you take the JAM exam, GATE exam, CUT exam, NET exam, this topic is very important. You can see at least one question from this topic. Okay. So thank you for watching with the Royal Chem Chemistry classes. Keep learning with the Royal Chem Chemistry classes. Okay, have a nice day.